Okay, we're going to get started now. We've got 4 back-to-back sessions, all in the research and technology track. And this is being live streamed, so at the end of the session, if you have a question, wait for us to bring you the microphone so the people at home can hear your question as well as the answer. The first session is on Cisco ONE, onePK, and our presenter is Kevin Woods. He is Director of Project Management at Cisco Systems. He is responsible for several of Cisco's key software-defined networking product lines, including One Platform Kit and OpenFlow. Kevin has a passion for emerging technologies and has been an early participant in the Ethernet network management, DSL, voice over IP, and software-defined networking markets. Again, Kevin will be presenting on Cisco ONE, onePK.
Thank you. So I work with a team of about 3,000 software engineers at Cisco. And if you operate a network that contains Cisco routers or switches, and as many of you probably do, and if you're interested in software-defined networking or OpenFlow or both of those things, in the next few minutes I'm going to show you some new things that you're going to be able to do with your Cisco equipment coming soon. And I only have 30 minutes, so I'm going to move along pretty quickly, and let's get started. First of all, software-defined networking and what are we doing about that? Well, there's a lot of different ideas for what software-defined networking is, and depending on who you talk to, you sort of get a different story, a different point of view. But I think the important thing about software-defined networking is what do people actually want to do with it. And since I work at Cisco in software-defined networking almost exclusively now for several years, I've had the chance to speak to a lot of different users about software-defined networking and OpenFlow in academia, in financial markets, all over the world. And here are some of the things that I've heard, that I would say the most common things that I hear that people want to do with this type of technology. First of all, they want to customize their routing. So we've had these protocols for years and years that automate route algorithms, calculation of routes and paths in the network, and we haven't really provided access to those algorithms unless you significantly modified the software in your device, and a lot of our users want to be able to do that. They'd like to process traffic in some custom way, be able to look into the tuples of traffic and analyze it and perform certain types of actions based on that. The ability to implement policy or security consistently across all the devices in the network, and to be able to do that in an automated fashion. That's a common request. Virtualization and domain isolation. So we've heard a lot, and probably some of you are familiar with network slicing, flow visor, the things that we're doing in the OpenFlow research community. That's another common use of software-defined networking. Federating control points, so boundaries between the LAN and the WAN, where we may have a service that traverses both of those networks, being able to have some higher level intelligence that can understand how to connect the traffic flowing in the WAN, let's say, for example, to an application or service that may be operating in the data center. And last but not least, very commonly, people simply want to be able to automate the provisioning of their systems. So this is pretty common in high-density data centers where you may have hundreds, if not thousands, of switches that are configured in exactly the same manner. And the users would like to be able to automate the provisioning of those and not have the human have to do that in every single case. So those are common applications. Let's take a couple of different perspectives on software-defined networking. First of all, the way that application developers in organizations view the network is if they have a problem with an application or deployment of an application, they view that as something that they can do relatively fast. With modern programming languages, it's not too hard to write software these days. We have a lot of skill. coming into the market, and so you can solve problems very rapidly by simply writing software. But when it comes to the network, many view the network as slow. If you want to change the configuration of the network, you want to change the network behavior, it's a special skill. It's viewed as difficult to do. It's viewed as slow. And so what we want to do is create a new paradigm where we can get the benefits of software development into the way that the network operates. And this is a big desire amongst those that want to deploy software-defined networking. Let's take another perspective on software-defined networking. So commonly, you'll hear the view that, well, software-defined networking is about separating the control plane and the data plane in the network. So in other words, instead of having these vertically integrated switches and routers that have a lot of software content, why don't we take the software, take the intelligence out of the device, centralize it somewhere, and then deploy relatively low-cost switches? So that's a common point of view. Sort of, you can see over here on the left-hand side, sort of the traditional integrated point of view. And then in the center, well, we took the intelligence out and we centralized it, and maybe we have a few logical intelligence entities that are speaking with each other. And what we really believe needs to happen is a combination of both of those things, where some of the intelligence is centralized and then some of the intelligence is also distributed. And well, what do we mean by that? Well, there are different examples. If you're trying to do something that needs to be, let's say, topologically aware of a very large network and needs to maybe calculate the best path for traffic to flow, it might be good to have that type of intelligence centralized. But if you have some type of intelligence that needs to make a local decision to select an alternate path, perhaps in the case of a failure, analyze some sort of local traffic or maybe some points of congestion in the network, that type of intelligence, you really want that to be distributed. And so what we need to do with our routing and switching software is be able to provide you the choice to do both of these. Consolidate, centralize some intelligence, and distribute other intelligence. So how do we do this? What is this new paradigm that we're seeing called software-defined networking? Well, a lot of this is about giving programmers application programmatic interface APIs into the operating systems and software in the network that gives that puts the control of the network into the hands of a qualified developer. And so we're introducing this concept throughout our software and providing these APIs so that you can do the use cases and you can do the centralization that we were talking about. And I'll show you more about that. Custom routing, custom traffic analytics, special security functions, things of this nature, which have been traditionally difficult to do with the types of interfaces we've provided to date. Easier in the sense with APIs. Now, where do these APIs appear? And what types of devices do we make use of these APIs? Well, we call this the Cisco Open Network Environment, ONE. And we place these APIs on our physical routers and switches, on our virtual routers and switches, and also in what you may think of as traditional controllers and agents for OpenFlow. To provide those functions, custom routing, et cetera, resource orchestration, what have you, these APIs are fundamental to making this open network environment work. So Cisco's way of doing software-defined networking is what we call Cisco ONE, the open network environment, and this is where we're deploying these functions. Now, taking another look at this, there is a lot going on in the standards arena on a few different fronts, and I'd like to talk about that for a minute. So We have the Open Networking Forum. Probably many of you are familiar with that. And the Open Networking Forum is the body that's defining the open flow protocol and a number of closely associated protocols met for manageability and other functions to support open flow. But that's not the only thing going on in the software-defined networking space. We also have a number of other activities going on. So we have in the IETF, for example, there is a new working group called I2RS, the interface to the routing system. And this is a control plane, data plane protocol as well that's being standardized, and we're working on that. If you look at software-defined networking broadly, you would also consider orchestration protocols to be in the software-defined networking space. They work off the same principle. And so we have OpenStack, for example, in the OpenStack forum, where we're significantly involved. But there's also open source frameworks. So for example, there's things like Chef, there's things like Puppet from Puppet Labs, and these are technologies that allow you to use software-defined networking like techniques in the orchestration space for resource orchestration, but in the using an open source model. So we feel that the software-defined networking will make progress on all of these fronts, and we're participating in all of these things. Now, I'd like to home in on one aspect of what we're doing with software-defined networking, and this is a product from Cisco that we call onePK, one programming kit, one platform kit. This is a new toolkit that we've developed within the operating system that allows you to automate, to extend, to innovate, to create new types of applications, and to compile those applications and have them run right on the device or in close association with the router or switch. And we're going to explain how this works. So over at the left, we've had this traditional approach of how you control the routers or switches in a network. And most of the suppliers in this space have followed this method. Typically, there's a command line interface, or there's a simple network management protocol interface, SNMP, or we've provided other interfaces, AAA, XML, and others. Additionally, we've often offered external network management systems or element management systems that make it easier to operate the network through these interfaces. And all of that's going to continue to be in place. None of that's changing, none of that's going away. But what the market wants to evolve to is this new paradigm over on the right, where we can write C or Java applications instead of just interpreted languages or scripts. And we can write complex software that operates right within the device itself or modifies the operating system within the switch or the router. And this is what we're able to do with onePK. So what's the difference? What's the real advantage of going over to this new model for programming our devices? And the advantages are a few. First of all, because you're programming in a compiled language like C or Java, you can write more easily, you can write much more sophisticated business logic. The second thing is that the scripting languages or protocols over on the left tend to be device-specific. In a programming environment over on the right, you can talk to and control multiple network elements simultaneously. And then lastly, that business logic that you write, that application that you write, can communicate not only with the network devices, but it may also communicate with some other external system. So let's say that you have an external system that is aware of the costs or performance needs of the network, or let's say you have a big data environment and you know that at a certain time of the day you're going to transfer a whole bunch of data from point A to point B. Well, the network doesn't necessarily know that. But through these programming languages and these interfaces, you can make the network aware that you're going to, let's say, move a bunch of data at a certain time every day. And you can prepare the network or optimize the operation of the network so that that works much better and much more cost effectively. And that's the advantage that you really get with using a programming language to control the devices instead of scripting. So how does this work? First of all, there's an RPC infrastructure that's built into the devices. And down below, we are representing all of the different types of Cisco devices that we have. So onePK is operating in all of those operating systems, those 3 operating systems. And that's taking calls or instructions from a central programming environment that we call the presentation layer or the abstraction layer up above. And in this abstraction layer and presentation layer up above, this is where the developer writes their application code, tests it, simulates it, compiles it, and then links it to procedure calls that speak directly to the devices or multiple devices. And this is basically the architecture and how it works. So that allows you to do a bunch of different things, this 2-layer architecture. For one thing, it allows you to separate the application logic from the device. So for example, you can take an application that you've written that controls the switch or the router, and you can run that application in a container on the processor of the device, or you can run that application on a server that may reside in the device as a blade, or you could operate that application on a separate server. And if you see the little yellow lines here, you can see how that application can communicate through this RPC channel to the devices and control them. So we have an API. And so now what can this API actually do? What sort of functions can it provide? What sort of things would I want to write in my application code to control the device? And here's a few examples. We have about 1,000 APIs available today. We've grouped them into categories so that the developer can a little more easily find the function that they're looking for. And you can do a lot. So you can go in and modify the data path directly. So you can copy packets, punt packets, you can inject packets back into the network. You can take those packets out and modify them in some ways. You can apply policies. So we give you API access to the policy engine that we've built into the system, so you can modify QoS or do special traffic analytics using the policy policy API set. Up at a higher layer, routing, we allow you access to the RIB, so you can get RIB events through the API. You can program the route information base. You can replace routes and overwrite them. A lot of capabilities provided there. The element API set allows you to look at very specific statistics, very specific counters within a port or a blade in the device, and give those statistics to your application. We have topology services, so you can discover neighbors, you can build the topology of the network. One of our early customers, North Carolina State University, actually wrote their own topology mapping application using onePK, and they use it to manage all of their resources, which are distributed over a large geographic area. They were able to write this application in about a week. Utility service set and the developer service set, also for supporting your applications and performing certain functions. The developer service set allows you, for example, to write your own CLI for your application that you're deploying. And then you can train your users how that application works and how to use the CLI to control that application. So there's really a lot of capabilities that we're providing you with a great deal of depth. Now, I've got a few use cases here, but since I see we've got about 10 minutes left, what I would prefer to do is actually show you a recorded demonstration from one of our programmers, Jason, who does a good job explaining explaining how onePK works, and actually shows you an application that he wrote, and he shows you what he can do. Let me see if I could just get this set up here. It worked before.
This is Jason Pfeiffer with another onePK demonstration. Now this demonstration uses a RESTful architecture to demonstrate a onePK application. Now REST is an architecture that's commonly used for the web, and how it is usually implemented is it allows you to traverse an HTTP URL path, and as you go to different elements in that URL path, the mechanism behind the web server converts that URL path to API calls, which are, in this case, onePK API calls. So just by traversing down to a specific URL, we're able to make changes to the network elements that we are connected to. And how this demonstration works is we have a simple network. We have a ping client, we have two network elements in between, and then we have a server that we're pinging to. And what we'll do is we'll make a REST API call by clicking on a web portal here. And as that REST API call is made, it'll apply policy to any 100, and we'll see the speed of the pings change. So you can envision this demonstration as something a service provider could use. Say they have a web portal to a customer that allows them to select different bandwidth choices. So here we have a website. It says select your bandwidth of choice. You have a low option, which has a maximum rating of 8 kilobits per second at $20 a month. Or the customer could choose a medium bandwidth, maximum rating 50 kilobits per second at $40 a month, and then a high rating, 200 kilobits per second at $60 per month. And here in this window on the left, I'll show a ping speed going through. And as we select different bandwidth choices, we'll see those pings change. So currently it's running in the low speed. You see the pings going slow. We'll click on medium, and that in turn makes the REST API call to speed up that ping. So you can see now that the ping's going at a medium speed. And the pop-up window that we show is the actual REST call that was made to change that policy. So what this shows is we've connected to network element 10.1.1.4. We've applied the policy with an identifier of 99, and it has an action to shape traffic to a rate of 50 kilobits per second. Now we can do the same thing with high. Close this window, click on high, and now we see the pings going really fast. So basically what we've done now is just shape that traffic up to a rate of 200 kilobits per second. So a real simple demo, but shows the power of onePK. Again, the ability to tie in with third-party tools and architectures, in this case using REST to convert to onePK API calls, and do some manipulation of policy based on those calls. And that concludes the demo. Thank you.
So Jason's pretty humble there. It took him about a week to write that application using Java. It's just a few hundred lines of code. It's using a REST interface to onePK. There's no special network management system that's used, no special product bought from Cisco, nothing. He just used a standard ISRG2 with the onePK operating system and programmed away, compiled the code. He actually told me he spent more time diddling around to try to get the graphics on those buttons right than he did trying to figure out how to program the switch. So this is a pretty easy tool to use, and as you can see, it's pretty powerful. So I went through a lot very fast. Sorry, I moved along very quickly, but we have a table set up outside, and we've got a few local representatives from Cisco here, including myself, that can help answer any questions that you may have. I think we've got time maybe for one, maybe two quick questions before we have to move on to the next section. Any quick questions that maybe we can take care of just before we move on? Okay. Well, I hope you learned something from that. I hope it was clear, and thanks a lot for your attention. Appreciate it.